Welcome to our math series, basic series on field theory. Today we're going to talk a little bit about polynomials. So, a polynomial given any field f. So, a polynomial is a very well-known concept. It's an expression of the form some finite addition of powers of x and x to the n plus a n minus 1 x to the n minus 1 dot, dot, plus a 0. We defined the degree of polynomial, so degree f of x equals the highest power of x, so here it'd be n. And we say this symbol signifies the set of all polynomials over some field f. And so these, for polynomial to be over the field f, just means an minus 1, dot, dot, a0 are all members of the field f. So we're going to define addition and multiplication for our polynomial things that we have here. We're going to assume, so we have two polynomials, f of x, g of x. We're going to assume n is greater than or equal to m. So we define f of x plus g of x is just we add each for power x of I, we add a of I and b of I. That becomes a new term in front of x of I. So the sum from I equals 0 to n of ai plus bi times x to the I. That's a coefficient now of x to the I. And note that if n is greater than m, then bn is just 0. F of x times g of x will be now a double sum. This is just like an ordinary polynomial multiplication. So the sum from I equals 0 to n plus m. And in that sum from j equals 0 to I, aj, bi minus j, x of I. So we just make sure these two coefficients added gives us I for the term in front of x to the I. And then again, note that if we say have bm plus 1 is just 0. So for polynomials over a field, we have division algorithms. So this is the usual division algorithm you would see in a high school algebra class. Although now we're doing it more generally over fields. We can do it for any field. So we have two polynomials over fields. We can find something, an equation of the form f of x equals q of x times g of x plus r of x. F of x, g of x are any two given polynomials. So we can find q of x and r of x, both polynomials, such that the degree of r of x is less than the degree of q of x. And so this is something we can prove. First note, if the degree of f of x is strictly less than the degree of g of x, then we can just add the remainder to f of x and q of x equals 0, and that would satisfy our equation. If f of x is a first order polynomial, so a1x plus a naught, and g of x is also first order, we can set q of x equals a1 over b1, and then the remainder will be a naught minus a1 times b naught over b1, and that will satisfy our equation. Also note, if g of x is just a constant, then divided by a constant, we clearly get that will not be an issue. And now we're going to proceed by induction. So we're going to assume we showed for f of x, degree of f of x equals 1. Our equation works just fine. So now we're going to assume degree of f of x our equation works for degree of f of x is less than or equal to any degree less than or equal to k. Our equation is satisfied. So we want to show for a degree of f of x equals k plus 1, we can still satisfy our equation. So assuming by induction we have our form f of x equals q of x, g of x plus r of x for degree of f of x less than or equal to k. Now we're going to assume f of x is degree k plus 1. So it equals a k plus 1, x k plus 1, dot, 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 plus a naught. K plus 1 is not 0. We're going to make a new polynomial f prime of x equals f of x minus a k plus 1 over b of m x k plus 1 minus m g of x. So note, g of x in this case is just b of m x of m times x to the m plus bm minus 1 times x to the m minus 1, etc. So note the polynomial on the right, the leading coefficient of f of x and the leading coefficient of this term on the right will both be ak plus 1 times x to the k plus 1, so they will cancel. So f prime of x is of degree no more than k. So by induction, we have f prime of x equals q of x times g of x plus r of x, where degree of r of x is less than degree of g of x. And so plugging in for f prime of x, our expression, we have f of x equals q of x plus ak plus 1 over b of m times x to the k plus 1 minus m times g of x plus all that plus r of x, where degree of r of x is still less than degree of g of x. And so that completes our induction, and that completes our proof. We can also show that these q of x and r of x have to be unique in this expression. So say we have two different expressions, f of x equals q of x, g of x plus r of x, and another expression where we have q prime of x and r prime of x. So subtracting these two, we get 0 equals q of x minus q prime of x, g of x plus r, the difference between the r of x's. And so here we still have degree of g of x is greater than the degree of r of x minus r prime of x. And so note, if q of x does not equal q prime of x, so this thing, q of x minus q prime of x is not 0, then since the degree of g of x is greater than the degree of this term on the right here, then we'll have a leading term on this left summoned, whose power is going to be greater than any power of the terms in the polynomial on this side will be. So that means this whole thing will not be 0 if q of x does not equal q prime of x. So that means q of x must equal q prime of x, and so q of x minus q prime of x is 0, so 0 times g of x is all 0. And so we're left with r of x minus r prime of x equals 0, and so r of x must equal r prime of x. And that's it. Thanks for watching. If you like this video, please check out the other Center of Math Field Theory Basic videos. Please check out our blog, check out centerofmath.org, and follow us on Facebook and Twitter. Thank you.